Okay, we're going to talk about rates of change and introduction to derivatives homework. All right, let's start with number 1. And we are talking about a rate of change. And in class, we talked about that rate of change or changing as a delta. And we're going to talk about the area, delta A, over our side length, delta S. And that can also be referred to as rate of change of A over the rate of change of S, and it's really, you're going to see that more so than anything else is the second way of writing it. And so that's going to be equal to, and keep in mind you're talking about the area of a square from 1 to 5. So we're going to talk about not D, my gracious, the area at 5 minus the area at 1 all over 5 minus 1. Now we're talking about the area of a square. So the area of a square, that side is going to be 5. So that's going to be 5 squared. So I have 25 minus 1 all over 4. So it looks like we're going to have a rate of change, average rate of change of 6. Now for the next, the surface area formula is going to be 6 times the side squared. And it's the same idea. We're talking about the rate of change of A over rate of change of S. And so we're going to have A at 2 minus A at 9. And notice I've got these backwards, but it's because we are decreasing. And that's going to be all over 2 minus 9. And so our surface area at 2, when I plug that in, that's going to be 4 times 6, so 24, minus, and if I plug in 9, we're going to have 6 times 81, aren't we? And that's all going to be over negative 7. And so after we do all of the numbering, you're going to end up with a 66 for your rate of change, but we need to know that this rate is negative. That's important. All right, moving on. The third one here is going to be the area of an equilateral triangle. That area formula is going to be the square root of 3 over 4, and that's going to be times your side squared. Takes me a minute to remember all these. Now you don't have to remember them. If anything like that comes up on the AP exam, they do give you these formulas. So don't be worried about learning formulas. You won't have to. So again, we're talking about the change in the area with respect to the change in the side length. And so we're going to have A at 4 minus, because we are decreasing, A at 12, and that's all going to be over 4 minus 12. Okay, and so finishing out the problem, we are going to get 16 on the square root of root 3 all over 4, minus, and then 12 squared, that's your side length, is 144 square root of 3 all over 4. And then every bit of that, that's all the numerator, is going to be over negative 8. And when we plug this into our calculators, we are going to get 4 on the square root of 3. And that, again, is your rate. And then y'all can type in and find your decimal. And keep in mind that this rate should be negative. And the next problem, we're going to be talking about the volume of a sphere. So very quickly, that volume is 4/3 pi r cubed. And again, you don't have to remember that formula. Those will be given to you. And so we're told that the volume of a sphere increases as the radius increases of the sphere. And notice that we're finding the average rate of change. So we have dV, the change in the volume, over the rate of change in the radius. And that is going to be, for this one, we're going to have our volume at 8 minus our volume at 1, or at 3, sorry. and that is all over 8 minus 3. And so whenever we put all of this in our calculators, we should have 2048 pi over 3 minus, and then we're going to have 108 pi all over 3, and then every bit of that is going to be over 5. That's your 8 minus 3. And so typing all this in your calculator, you should get approximately 406.313, and of course that rate of change is going to be positive. All right, and so let's look at the next one. And we have, let's see, after a drug is injected in the bloodstream, the effectiveness decreases slowly over time. So it looks like our rate would be negative because it is decreasing. And we have C at T is going to represent the drug concentration. So we're looking for an algebraic expression over the period of time from 0 to 4. So I'm looking at our change in C over our change in time, or this could be written as dC over dt. All of that's the same, and we don't really have a specific formula here, so the best we can do is say that we would need to find our concentration at 4 hours minus the concentration at 0 hours, and all of that would be over 4 minus 0. And so since we don't have a formula, that's the best we can do for that one. For our next problem, we're going to look at this equation that we're given, and that equation is going to model the height that the golf ball is off the ground. And notice the very first question here, they ask us to draw a line tangent to the curve at 4. So we're going to go up to where 4 is on the graph, and when we draw a line tangent, remember we're only going to touch the graph in at most one place. Now it might run really close and parallel, but it's not intersecting that graph at all. So we're touching at one point, and then notice number 7 asks us to estimate the instantaneous rate of change at time t equals 4. And so in order to do that, we're going to have to really get a very tight interval around this 4. So several different ways we could do that. We could use our time frame of 4 and a little bit before it, so maybe 3.9 would be a good number to use. Any number really close to that 4 should produce something that we need. And so we would need to look at our height at 4 minus our height at 3.9, and that's all over 4 minus 3.9. And so after we put all of that in our calculators, we should get something that is approximately negative 18.8, and our units would be feet per second. And then for number 8, it asks us what is the mathematical name for this instantaneous rate of change. And our mathematical name for this would be a derivative. So our derivative, that's going to be our instantaneous rate of change. Now, why is this rate of change negative? Well, the height of the golf ball is decreasing, so the rate would be negative. So again, let's put this in a good sentence here. So the rate is negative because the height of, and this was a golf ball, is decreasing. All right, so there's a great problem that is going to show us how to really approximate our derivative value using our average rate of change, or the AROC formula, and we're using that to approximate the derivative. Okay, for the next one, Amy was walking to the bus stop. When she saw a bus approaching, she started to run toward the bus but couldn't catch up. The bus left before she could get there. So Amy walked all the way to school. Okay, so we need to draw a distance and time graph for this scenario. So again, we don't really have for sure time values, but notice that over a time Amy was walking to the bus stop, so she's probably just la-da-daing around walking to the bus stop. And then after she saw the bus coming, she really picked up her speed. So the slope of this is going to get steeper because she changed her pace. And then after she couldn't catch the bus, well, then she probably just slowed back down and just strolled her way back to school. So that's all this was talking about. And notice we just represented this linearly. So there's not just a whole lot more to that one. Okay, number 11 is talking about raccoons, and we will talk about all kinds of animals. So we have a raccoon. The population varies due to fluctuating food supplies. Assume the number of raccoons R at T is given by this function, the sine function here, where T is time in years. Store the function. So this is going to be talking about our calculator, and so we don't really necessarily have to store all of this, but we do need to pay attention that we're going to use the window from 0 to 10, and we're going to sketch the graph that we see, and then we are going to look at our increasing and decreasing intervals, and maybe a place where we might not be changing. So if we graph this, since this is a sine curve, it's probably going to do something like this. Okay, and so as we continue, I guess I could finish this out. Now let's look at what we could do with our tangent lines across this graph. If I had to sketch a tangent line here, notice that the slope of this line would be positive while my graph is increasing. And that's not just an accident. That's going to be true nearly all the time. So here, notice that my function's increasing. So if that function is increasing, notice that the slope of the tangent line, so the slope of the tangent is positive, is greater than 0. Well, what could we say about the decreasing function? Well, on this side, notice that the function is decreasing, and if I draw a tangent line on that graph, notice that the slope now of the tangent line is going to be negative because this is decreasing. So when the function is decreasing, the slope of that tangent line is going to be negative. And then notice where it says not changing much. So that's going to be somewhere, I need to change colors, sorry. If we look in the area, let's say we've got a tangent here. Well, or we could even look at the tangent, let's say it's sitting up here. Notice what's happening there. We know that the slope right here, for sure we can pinpoint that slope is 0. So right here, notice we're not changing much at all. Now every time we talk about all of this increasing and decreasing and the slope of the tangent lines, we can really associate the slope of the tangent line is the instantaneous rate of change, which is the derivative. Very important that we connect all of those. Very, very important. Okay, so for number 12, it's going to ask you to estimate the average rate of change of the raccoon population for 1. The change in R at T from year 1 to T is R at T minus R at 1. Now complete the values for each of the following. So which is the best approximation? So the best way to approximate at year 1 would be if our time frame is T equals 1 and we had to do some kind of estimation, I would let, of course, one side of it be 1, and then I would look at our average rate of change from 1 to T equals 1.01. Something of that nature. That should be our best approximation. So now let's look at part B, because again, they didn't ask us to find it. They just said, okay, what would be the best approximation to use? So looking at part B, what does this rate mean regarding the raccoon population? Well, we do need to fill in, and if we go through and type all of this in our calculators, our R at T value for the first one, we should get 81.610. And then the next one, we should get 80.478. And then we should get 74.605. So based on those, what does that mean about the raccoon population? So notice with each one of these values, we have a positive value in any of those little intervals, and we can even increase or make the interval smaller around 1. And notice that all of these rates of change are positive. So if they're positive, then we know from above, looking at the previous example, number 11, that the raccoon population is increasing at T equals 1 year. Now, we're not comparing this number to this number to this number. Notice we can say that the population is increasing because this rate is positive. And I'm going to put that in parentheses because that means you don't have to write that on the AP exam. But it's good for us to know as we're learning this. And again, it's because the rate is positive. That's why. So be careful, don't be misled by the numbers. You're just looking at the sign of them. So number 13 says the instantaneous rate of change of R at T equals 1 is the limit R at T approaches as T approaches 1. So use the numerical derivative feature to determine the instantaneous rate of change. And we could find the derivative at 1, and we will look at that. So it should be a pretty close approximation to what we already have. When we do type this in our calculator, we're going to see R prime at 1. That's our notation for the derivative or the instantaneous rate at T equals 1. That's the notation. It is going to be approximately 81.045, and again we need our units, and that was raccoons per year. Okay, and so then now the next one, approximate the instantaneous rate the raccoon population is changing at 4. Okay, so here if we go through, and we really need a real tight interval around this, so I would do R at 4 point, I don't know, well, let's throw in a couple of zeros, minus R at 4, and of course that's all going to be over 4.001 minus 4, and so that, once we put that in our calculators, is going to be approximately negative 98.364. And that's going to be, again, our units. We must include those. We don't need to drop those. And that's going to be raccoons raccoons per year. Now, notice we got a negative rate. And so what would it mean if I do all this and I get a negative rate? Well, that would mean that the population of raccoons is decreasing. And that is definitely important. We have a negative rate, then we know that whatever we're approximating is decreasing. And here it was approximating the population of raccoons. All right, so for our next problem, we have the number of E. coli cells, P at T, at time T hours in a petri dish is plotted to the right. So now we know what that graph is. In the first part, A, it tells us to draw a secant line over the time interval from 1 to 3. So notice we have here, we have the point 1, 2000. And then at 3, we have the point here, which is going to be 3, 8,000. So we need to sketch our secant line through those points, and we're just going to pretend that line is straight because we know my amazing drawing skills. It's not the best in the world, but it's pretty close, so we'll let it go. All right, so here we need to calculate that average rate of change. So again, that's just going to be the slope of that secant line. So I'm going to write that in as another reminder. AROC is the slope of the secant line every time. So our slope formula here, we would take our y2 minus our y1, or f at b minus f at a, over b minus a. And then that's going to give us, if we number crunch all that, we're going to end up with 3,000. And this was bacteria per, and what was the time per hour? All right, so now let's look at the next one. And the next problem tells us to estimate the instantaneous rate of change. So that means IROC, which is the slope for the tangent line. So at the point 1, 2000, using the tangent line passing through the point shown. So the point that they're pointing out to us right here, so that would be at the point 4, 6,000. So we need to estimate our instantaneous rate of change using this. So we are going to go back and set up our AROC, because again, this is a great example of using our average rate of change to approximate our instantaneous rate of change. That's what we're doing. So to set that up, we would have 6,000 minus 2,000 over 4 minus 1. And so that's going to give me roughly 1,333 with 3 repeating. And that's going to be bacteria per hour. Okay, so notice, what does the slope, explain what does the slope represent in the context of the problem. So the slope here, and the way it's talking about is at 1 hour, so it's talking about our slope. So at 1 hour, and we were talking about the E. coli cells, and look at the rate. If the rate is positive, then the cells would be growing. If the rate was negative, they would be decreasing. So here the cells are growing, and again, we know that because our slope was positive. So they're growing at a rate of And that rate is the slope that we just found. So it's got a rate of 1,333.33 cells, or it was bacteria, but we can say cells per hour. So we can use the slope of that tangent line to approximate and narrow down a rate of change at a precise instance. Okay, let's look at one more example here. All right, so each position graph shown below represents the particle motion as a function of time. And we need to match each graph with the proper description. So notice in A, I would start with just the description and then go to the graph. So for A, we are talking about speeding up. So if we are speeding up, then we need to be increasing. Now notice this function increases, but then it starts to slow down a little bit. Now this one kind of gets a little strange here. It ends up here speeding up, and then slowing down. And then for the next one here, notice it looks like it's it's increasing, but then it's slowing down, and then it increases again. But look at this last one. That one is strictly increasing. So that one I would think is speeding up for sure. Okay, let's see, slowing down for C, slowing down. Well, this one is the one that looks like it's starting to slow down. So it's easing off. So that I think is going to be C. Now we have to look at the difference. In B, we're speeding up, then slowing down. But then D, we're slowing down, then speeding up. So for B, I think this one should be B. Because again, we're speeding up. So this is going to be a very steep slope. Whereas D, the slowing down, is going to be a smaller slope. So that's going to be D.